Today, we're going to talk about how to use CLIP for zero-shot image classification. That is image classification without needing to fine-tune your model on a particular image dataset. For me, this is one of the most interesting use cases that really demonstrates the power of these multimodal models. Those are models that understand different domains of information. Like for CLIP, for example, that is image and text. But how about other state-of-the-art computer vision models? How do they perform in comparison? Well, these other computer vision models, they are characterized by the fact that they really focus on sort of one thing in an image. So, for example, let's say we had a computer vision model that was trained to classify an image as to whether it contained a dog, a car, or a bird. Okay? That computer vision model doesn't really need to know anything other than what a car looks like, what a dog looks like, and what a bird looks like. It can ignore everything else in those images. And that's one of the limitations of the state-of-the-art computer vision models. They have been pre-trained on a huge amount of data, but they've been pre-trained for classification of these particular elements. And even if you have like 1,000 or 10,000 classes in there, that hardly represents the real world, which has a huge variety of concepts and objects for us to, as humans, to understand and see and categorize. So what we find with these computer vision models is that they perform very well on specific datasets, but they're not so good at handling new classes, for example. For that model to understand a new class of objects and images, it will need to be fine-tuned further, and it's going to need a lot of data, and it's not very easy to do. Ideally, we want a computer vision model to just understand everything would be perfect. Obviously, we're not quite there yet, but if it can just understand the world and the visual world relatively well, then we're sort of on the way to a more robust model. So, for example, with this image of a dog, we want the model to understand that a dog is in the image, and usually use a convolutional neural network. That sort of model for image classification will know that there is a dog in the image, but it doesn't care about everything else in the image. Ideally, we want it to understand that there are trees in the background. The dog is running towards the camera, it's on a grassy field, it's sunrise or sunset, and that there are some blurry trees in the background, a blurry street. Unfortunately, classification training, we don't get that. Instead, the models are essentially just learning to push their internal representations of images with dogs in all towards the same sort of vector space. That's essentially how we can think about this. And then, for example, earlier I said cars and birds as well. We could imagine, so they have like a cluster of dog images, they have a cluster of bird images, and they have a cluster of car images. But they don't really have anything else in between that. So this is ideal if we just want a yes or no answer for a specific data set and we want good performance. We can do that as long as we have the training data and the compute and the time to actually do that. However, if we don't have all of that and we just want good performance, maybe not state-of-the-art, but good performance across a whole range of data sets, that's where we use CLIP. CLIP has proved itself as an incredibly flexible model that can work in both text and images and is amazing at something we call zero-shot classification. Zero-shot basically saying you need 0 training examples for this model to adapt to a new domain. So before we dive into CLIP, let's just explain this zero-shot thing in a little more detail. So zero-shot comes from something called n-shot learning. N-shot, you may have guessed, is basically the number of training examples that you need for your model to perform on a particular new domain or new data set. Many state-of-the-art image classification models, they tend to be pre-trained on like ImageNet, and then they're fine-tuned for a specific task. So they have the pre-training, and the pre-training basically sets up the internal model weights of that model to understand the visual world, at least within the scope of the ImageNet classification set, which is fairly big, but it's obviously not as big as the actual world. And then those models are usually fine-tuned on a particular data set. And to fine-tune that sort of pre-trained image classification model on a new domain, you are going to need a lot of examples. Let's say as a rule of thumb, maybe you need 10,000 images for each class or each label within your dataset. That may be excessive, it may be too little, I'm not sure. But you do need something within that ballpark in order to get good performance. We could refer to these models, so these are like ResNet and BERT, as many-shot learners. They need many training examples in order to learn a new domain. Ideally, we want to maximize model performance whilst minimizing the N in N-shot. Okay, so minimizing the number of training examples needed for the model to perform well. Now, it's worth noting that CLIP is not achieving state-of-the-art performance on any particular datasets or benchmarks. Other than one, surprisingly, without seeing any training data for this particular dataset, CLIP did actually get state-of-the-art performance on that one dataset, which is surprising without seeing any of the training data. But here we go. This is how useful this sort of thing is. Let's talk about how CLIP makes zero-shot learning so effective. So CLIP stands for Contrastive Language Image Pre-training. It was released by OpenAI in 2021. And since then, it has done pretty well. We can find it in a lot of different use cases. This is just one of them. So CLIP itself actually consists of two models. I've discussed this in a previous video and article in a lot more detail. So if you're interested, go and have a look at that. For now, we're going to keep things pretty light on how CLIP works. But in this version of CLIP, those two models are going to consist of a typical text transformer model for dealing with the text encoding and a vision transformer model for dealing with the image encoding. Both of these models within CLIP are optimized during training in order to encode similar text and image pairs into the same vector space, whilst also separating dissimilar text and image pairs so they are further away in vector space. So essentially in that vector space, similar items are together, whether they are images or text. Now, CLIP distinguishes itself from typical image classification models for a few reasons. First, it isn't trained for image classification, and it was also trained on a very big data set of 400 million image to text pairs with this contrastive learning approach. So from this, we get a few benefits. First, for actually pre-training the models, training the model, CLIP only requires image to text pairs, which in today's age of social media, they're pretty easy to get. Any post on Instagram, for example, there's an image and there's usually a little caption of someone describing what is in the image. We have stock photo websites, social media, just everything everywhere. We have images and text usually tied together. So there's a lot of data for us to pull there. Because of the large dataset sizes that we can use with CLIP, CLIP is able to get a really good general understanding of the concepts between language and images, and just a general understanding of the world through these two modalities. And as well, within these pairs, the text descriptions often describe the image, not just one part of the image, like, okay, there's a dog in the image, but something else, like dog is running in a grassy field. Okay, they describe something more, and sometimes even describe very abstract things, like the sort of feeling or mood of a photo. So you get a lot more information from these image to text pairs than you do with a typical classification data set. And it's these three benefits of CLIP that have led to its pretty outstanding zero-shot performance across a huge number of data sets. Now, the authors of CLIP in the original CLIP paper, they draw a really good example using CLIP and the ResNet 101 model trained for ImageNet classification. Now, CLIP was not trained specifically for ImageNet classification, but they showed that zero-shot performance with CLIP versus this state-of-the-art model trained for ImageNet was comparable on the actual ImageNet dataset. And then when we compare them on other datasets that are derived from ImageNet, so you have ImageNet v2, ImageNet R, ObjectNet, ImageNet Sketch, and ImageNet A, CLIP outperforms the model that was specifically trained for ImageNet on every single one of those datasets, which is really impressive. Okay, let's talk about how CLIP is actually doing zero-shot classification and how we can use it for that as well. So CLIP, the two models within CLIP, they both output a 512-dimensional vector. Now, the text encoder, it can consume any piece of text, right? And then it will output a vector representation of that text within the sort of CLIP vector space. Then if you compare that text to an image also encoded with CLIP, what you should find is that text and images that are more similar are closer together. So now imagine we do that, but instead of, so we have our images from an image classification dataset, and then for the text, we actually feed in the class labels for that classification task. Then you process all that and then calculate similarity between the outputs, and whichever of your text embeddings has a high similarity to each image, that is like your class, okay, your predicted class. Okay, so let's move on to an actual applied example and implementation of zero-shot learning with CLIP. Okay, so to start, we will need to pip install datasets, torch, and transformers. And what we're going to do is download a dataset. So this is the FRG FM ImageNet dataset. We've used this a couple of times before, and it just contains 10 different classes. Not too much data here. We're looking at the validation set. So we have just under 4,000 items here. And if we have a look at what we have in the labels feature, so in the image feature, we obviously have the images themselves. Label feature, we have these 10 labels, okay, but they're just numbers, they're integer values. We obviously need text for this to work with CLIP, so we need to modify these, or we need to map these to the actual text labels. Now, we do that by taking a look at the Hugging Face dataset info, features, and then label names. Okay, so most Hugging Face datasets will have a format similar to this, where you can find extra dataset information like the label names. Okay, and then from there we can see we have Tench, English Springer, cassette player, a few different things. All of these map directly to the values here. So for 0 we would have Tench, 1 we would have English Springer, and so on. So as before, we're going to convert these into sentences. So a photo of a Tench, photo of a English Springer, and so on and so on. Okay, so from here, before we can compare the labels and the images, we actually need CLIP. So we can initialize CLIP through Hugging Face. So we use this model ID, and then we use the model processor, which is going to pre-process our images and text. And then we also CLIP model here, which is the actual model itself. And then we can also run it on CUDA if you have a CUDA-enabled GPU. For me, I'm just running this on Mac, so CPU. MPS, as far as I know, is not supported in full, or CLIP is not supported in full with MPS yet. So that's like the Mac M1 version of CUDA. For now, CPU is fast enough. It's not slow, so it's not a problem. Now, one thing here is that text transformers don't read text directly like we do. They need like a translation from text into what are called input IDs or token IDs, which are just integer representations of either words or subwords from the original text. So we do that with the processor here. Just passing our text. Padding we set to true so that everything is the same size. We need this when we're running things in parallel, like multiple inputs in parallel. Essentially when we're using batches. We're not passing out images here, and we're going to return PyTorch tensors. Okay, and we're going to move all that to our device. For me, it's just CPU, so it doesn't actually matter, but it's fine. And then here we can see those tokens. So we have a SotA sequence token here. And then we could imagine this is something like a photo of a Tench, something along those lines. And then end of sequence over there as well. So we can encode these tokens into sentence embeddings. All we do is this. So pass our tokens in here, label tokens. Now in here we have input IDs and also another tensor called attention mask, and that's kind of wrapped within a dictionary, which is why we're using these two asterisks here to iteratively pass both of those tensors as individual items to the getTextFeatures function. And then after we have our label embeddings over here, we just want to detach them from PyTorch gradient computation of the model and convert that into NumPy. And then we can see from that we get 10 512 dimensional embeddings. Okay, so they're now the text embeddings within that clip vector space. And one thing to note here is that they're not normalized. Okay, we can see they're not normalized. So we can either use cosine similarity to compare them, or we can normalize them and then we can use dot product similarity. Now, if we normalize first, I find the code later on to be simpler. So we will do that here. So we're going to normalize here. It's pretty simple. And then we can see straight away they're normalized. We can just use dot product similarity now. That's the text embedding or the label embedding part. Now what we want to do is have a look at how we do the image embeddings and then how we compare them. So we're going to start with this image first, just a single image. We'll go through the whole data set in full later. So we just have a cassette recorder here. We go down here, we're just going to process the image. So using the same processor, we set text to none because there's no text this time. And what we want to do is just pass that image in here to images. And we're going to return the tensors. It's PyTorch tensors and extract the pixel values. Now the reason that we have to process the image is Clip expects every tensor that it sees to be normalized, which is the first thing it does, and also a particular shape. It expects this shape here. So 3 color channels, which is through here, a 224 pixel wide image and 224 pixel height image. Okay, so all we're doing there, normalization and resizing. And then from there, we can pass it to get image features. Image again, like here, we didn't include the iterable because this is just a single tensor. We don't need to pass the 2 asterisks here. And we get a single embedding here, 1 vector, which is 512 dimensions. As with our label embeddings, we're going to detach them, move them to CPU, and then convert to NumPy. I already have them on CPU, so this part isn't necessary, but if you're using CUDA, it will be. And then we don't need to normalize them. So when we're doing dot product similarity, we just need one side of the calculation to be normalized, not both. Okay, so with that, we do NumPy dot. We have our image embedding, and then we transpose the label embeddings. And you see that we get scores, and the shape of those scores is one dimensional. That's not important. Here we have those 10 similarity scores. So 1 similarity value for each of our 10 labels. Okay, so then we can take the index of the highest score, which happens to be index 2, and then we find out, okay, which label is that? It is cassette player. Okay, so it's correct. That's pretty cool. Now, let's have a look at how we do that for the whole data set. So all I'm going to do is we're going to go through in a loop through the whole data set. We're going to do it in batches of 32. Process everything. This is all just the same stuff. Okay, process, get the embeddings, get dot product. Okay, we don't need to redo this for the labels because we just have the 10 labels throughout the whole thing. So it's not necessary. We'll get the argmax, and we're just going to append or extend a prediction list with all of those predictions. Okay, and let's see what we get. Well, let's see what the performance is there. So here, calculating how many of them align to the true values. And we can see we get 0.987. Okay, so that means we get 98.7% accuracy, which is pretty insane when you consider that we have done no training for Clip here. It has not seen any of these labels. It has not seen any of these images. This is like out of the box, 0-shot classification, and it's scoring 98.7% accuracy, which is, I think, really very, very impressive. So this is, I think, a good example why I think zero-shot classification or image classification with CLIP is such an interesting use case. It's just so easy, right? You can do this for a whole ton of data sets and get good performance. It's not going to be state-of-the-art performance, but pretty good performance like this. Super easy. So before CLIP, as far as I'm aware, this sort of thing wasn't possible. Okay, every domain adaptation to a new classification task needed training data, it needed training, and so on. With this, it's just a case of you need to write some labels, maybe modify them into sentences, and then you're good to go. So that's why I think CLIP it has created a pretty big leap forward in quite a few areas, such as image classification. So when I think of CLIP, there is in the short time that it's been around, we have multimodal search now, zero-shot image classification, object localization or image localization, object detection, also zero-shot, and we'll go into that in more detail pretty soon. And even industry-changing tools like OpenAI's DALL-E includes a CLIP model. Stable Diffusion, as far as I know, also includes a CLIP model. So there's this massive range of use cases that CLIP is being used for, and I think that's super interesting. So that's it for this video. I hope you have found all of this as interesting as I do. So for now, thank you very much for watching, and I will see you again in the next one. Bye.